All right. You're welcome, members, our viewers, all viewers from all continents. You're welcome again. It's me, Mr. Hyper, and I'm taking you through alkylation and acylation of benzene. This is our lesson 3 of organic chemistry. Now, let's begin with the alkylation of benzene. Members, by simple terms, when we say alkylation, we are simply meaning introducing the alkyl groups in the benzene ring. So if one talks about alkylation, look at it as the introducing of alkyl groups in the benzene ring. So now, if it is the introducing of the alkyl groups in the benzene ring, then now you need to know that the reaction will take place with a haloalkane mixed with benzene in presence of a catalyst called the halogen carrier. So here we are having the alkyl groups, all right, where we are going to have a haloalkane mixed with benzene in presence of a catalyst, which is the halogen carrier. For example, here you have benzene ring. Bromomethane. Now this is our haloalkane. This is bromomethane. So now this one takes place in presence of the halogen carrier, and the halogen carrier that we are going to consider in this case, let's use ammonium bromide for the start. Ammonium bromide, and this reaction takes place at room temperature. So we're going to form methyl benzene. This reaction leads to the formation of methyl benzene. So CH3 and hydrogen bromide. This one we've called it methyl benzene. Now, what takes place with this process is that the haloalkane, this bromomethane, is going to react with a halogen carrier, the ammonium bromide, so that we form an intermediate which contains the electrolyte that will attack our benzene ring. So when we are doing, or when we are suggesting a mechanism, in outlining of a mechanism, we shall have our CH3 Br plus ammonium bromide, and this one will lead to the formation of CH3. This is partially positive, and this one will be ammonium bromide, which will be partially negative. So that is what we specifically have. You need to first get that haloalkane. You react it with the halogen carrier so that you get an electrophile. So now it is this electrophile that you are going to bring to participate in the reaction. Now, what we do, we shall have our benzene ring. Then we bring our methyl group. So when this bond comes to methyl group, this one will break off, leading to the formation of, we said that when the electrophile attacks the ring, this one becomes unstable, and there is a bond that is formed between hydrogen and that electrophile that has been attached. Then at this point, of course, we had left with the aluminum bromide. So it is this aluminum bromide which will come on the hydrogen. The hydrogen will stabilize the ring. And this one will lead to the formation of methylbenzene plus hydrogen bromide and aluminium. The final products must be the normal products which you are aware about, because this is like an intermediate. It can't exist. You can't have aluminium with a bromide as a foil. It can't exist. It's just an intermediate, but as we terminate the reaction, you have to write the real products, whereby you can see that a bromide will pick a hydrogen, you form hydrogen bromide, and then what is left is aluminium bromide. So this is how we outline the mechanism, as simple as that. Now, you realize that the catalysts that we use generally in electrophilic substitution in the benzene ring were discovered by men, Friedel and Kraft, and therefore they are called Friedel-Crafts catalysts. And therefore, all these reactions that involve halogen carriers, all the catalysts are called Friedel-Crafts reactions. Okay, so also these alkylations can take place between benzene and an alkene. For example, propene in presence of an acid, right? There we shall use an acid and maybe a catalyst, which is aluminium bromide. It can be aluminium chloride, it can be any catalyst. But I wanted to bring to your attention that the reaction also can take place in the presence of an alkene with an acid. So let's see how the reaction takes place with alkenes. So maybe I can note and say benzene also reacts with an alkene. It reacts with an alkene such as propene. All right, we can say such as propene in presence of an acid. This one takes place in presence of an acid and a catalyst. And the catalyst we can use maybe aluminium. Can use aluminium chloride. So in other words, the equation, this reaction is also electrophilic substitution, all right? But we are going to see how we derive an electrophile by ourselves. So here you have benzene ring plus we shall have propene all right. We say that this one takes place in presence of halogen carrier. We have said to use aluminium chloride, but you can use aluminium bromide, you can use iron-3 bromide, something like that. So here we shall operate in presence of an acid. So the product that we form here is simply, of course, we shall have a benzene ring. Then it is 2-phenyl propane. So we shall have CH3, right? Then 2. And this is what we call 2-phenyl propane. But the mechanism is going to give us the background of each and everything. So during the mechanism, this propene will first react with the acid, all right? So we shall have propene, CH3, CH2. And if it is reacting with the hydrochloric acid, one can look at the Markovnikov rule from alkenes. So here we shall have the hydrogen and we shall have the chloride or the chlorine atom, but this is partially positive, this is partially negative. A double bond is rich in electrons, therefore it attacks the electrophile as this one goes off. So this one will lead you to form, you're going to form CH3, CH, we shall form CH with the positive, and then this one will form CH3, then plus a chloride, but this chloride can come here so that we form our CH3, but CH3s are 2 times, so we shall have 2, then we shall form CH and Cl. So now this is the one that is going to react with our halogen carrier. So we shall have our CH3 2 times CH, then Cl. We shall add our aluminum chloride, so that will form our electrophile, and it will be CH3, 2, CH, all right? This will be partially positive, this is my electrophile. Then aluminum chloride. This will be my other intermediate. So now it is this electrophile that is going to attack the benzene ring. So you bring your ring. So we shall have it as our benzene ring. All right. So we shall have our benzene ring. Then here we shall have our CH3, 2 times CH. Here we have your aluminum chloride minus. So this will come on this positive carbon center as this one goes away. So this one will lead you to form benzene ring, but which is very unstable. Then the electrophile and the hydrogen will momentarily form a bond. Here we shall have a hydrogen, and here I can write this as CH, then CH3, 2. So it is at this stage, that you're going to bring your aluminum chloride to stabilize the ring. So we shall bring our aluminum chloride, which will come to hydrogen, and this hydrogen, the bond will stabilize the ring, and after stabilizing the ring, you're going to form a stable 2-phenyl propane, then plus we say that we shall form hydrogen chloride and the normal aluminum chloride. As simple as that. So before I take you to where we apply this, maybe I need to give you some other highlight on how this can be examined. This mechanism can appear in very many different ways. So it's a matter of mastering all the ways, and then you push very, very, very well. It's a matter of understanding all the ways, and then you push very, very wisely well. So we are going to look at other type of reaction that is undergone by benzene ring. So in short, here the alkyl group can be anything. Actually, it can be anything, and I'm going to give you something to practice, right? But before I give you something to practice, let me first carry out one of the mechanisms for you maybe that I think can be somehow challenging. So let me wrap this. I do for you one more. We can also have our benzene ring. And this benzene ring, when it is reacting with propene, and concentrated phosphoric acid, when we really don't have any halogen carrier. If you don't have any halogen carrier still, you're going to form the other same product. You're going to form the other same product, CH3 two times. So here, when you're outlining the mechanism, is very simple. And when you're outlining it, first work on the phosphoric acid, dissociate the phosphoric acid. So here you form hydrogen ions and H2PO4 minus. So now what you do, first bring your propene, CH3, CH, double bond, CH2. Now you bring your acid, the hydrogen ion. So what you will form, you're going to form the unstable ion, and then we shall have CH3. So what you do here, you are going to bring your ring, and then you bring this ion. So we shall have CH plus CH32. So we shall have something simple like that. And this one will lead to the formation of unstable ion. And here you will have the CH, then CH32 with the hydrogen. So it is this bond of the hydrogen that will stabilize. This bond of hydrogen will be the one to stabilize the ring. And here we shall lose a proton, we shall have proton loss, and automatically you will form your product as simple as that. So you can do these mechanisms in all ways you want. You can do these mechanisms in all ways you want. So maybe for these purposes, for this case, I'm going to give you some numbers to try as our viewers. You try and you practice. So let me rub off this. You're going to try for me the following. You're going to try for me the following. So amongst the equations which I want you to try is this exercise on that, your own practice, and I'm going to say complete the following equations and outline mechanism for each. The first one is when you have a benzene ring plus iodomethane under the conditions of aluminum chloride at room temperature. For your practice reasons, you can also try this, where you have benzene ring plus chloroethane in presence of iron 3 chloride at room temperature. Further, for your revision purposes, you can also try benzene plus propene in presence of any acid. So for your revision purposes, you can try those numbers and then you see how you can move life on. So this reaction, basically, the one we ended with, where we formed 2-phenyl propane, can be used also in synthesis or in manufacture of phenol. So I told you that at the end of each and everything, at the end of each and every mechanism or each reaction, we shall be looking at where does that one apply. So maybe let me note for you and say that 2-phenyl propane is used to prepare phenol. In the following ways, or in the following steps. So now we want to see in what steps does the other 2-phenyl propane be used to prepare phenol. Remember, our 2-phenyl propane was written as this. So it was CH, then CH3 2 times. So which can as well be written as, I do my benzene ring, then I put CH here, then CH3, and CH3. These are the same things. So this one, 2-phenyl propane, is oxidized. So it undergoes area oxidation for the peroxide of benzene. So we form a peroxide. And that peroxide, here we have our C. I'm following the structure here. Here we have our C, and here we have our CH3. I think I'm clear. Then also here we have our CH3. All right. Then I'm going to bring an O here, and then OH, whereby these two O's are for oxygen. They're forming a peroxide here, the hydroxyperoxide. Okay, the benzene hydroperoxide. So you are forming a peroxide here. Then the H which was here is the H I'm bringing down here. So now what will happen after forming this peroxide? This peroxide is going to be warmed with, we warm this peroxide with dilute sulfuric acid. The moment you warm that peroxide, then you form your phenol and acetone. So we shall warm it with dilute sulfuric acid. So when you warm it, you're going to form your phenol and acetone, because after removing the OH, you'll be left with the CH3CH3, which is acetone, or what we call propanone. So we shall remain with CH3COCH3. So this is what we call our phenol. And this is what we call our propanone or acetone. So members, these things are just as simple as this. You can outline this synthesis in a few steps, and really it is very, very, very amazing. So that is what we have. However, here maybe during oxidation there is some pressure and some temperature, but for purposes of knowing what it takes us to, the process is oxidation, then hydrolysis with an acid. Now that is what we have. Then from there, the last reaction that we are going to look at here is the acylation. We're going to look at the acylation after you have been looked at this, and after you have been practiced these three. Let me take you to acylation, and then we call it the end of these reactions of benzene that are electrophilic substitution. All right, so let me take you to acylation. Acylation of benzene. Acylation of benzene. The moment we say acylation, we are trying to mean the reaction of benzene and an acid chloride. This is the reaction between benzene and an acid chloride. And how does it proceed? Actually, acid chlorides, one can call them acyl chlorides. So, acyl chlorides may be, for our case, let's consider an example of ethynyl chloride. And that is CH3, COCl. And that reaction takes place at 50 degrees Celsius. And this reaction is basically used to yield aromatic ketones. Ketones are carbonyl compounds. So if we need an aromatic ketone, by acylation of benzene, we can easily get what we want. We can easily get the appropriate ketone depending on the number or depending on how many alkyl groups the acid chloride is having. So for example, here, if you have your benzene, we have our benzene plus ethynyl chloride, CH3, COCl. This one is going to take place in presence of aluminum chloride. And we shall reflux at 50 degrees Celsius. And this one, we are going to form our product, which is phenylethanone, because here we shall have our C, double bond O, then CH3. If you are not conversant with the product, you are also advised to first write the equation, rather the mechanism. First outline the mechanism, then from the mechanism, you can easily get the product. So it's not a must that you must be knowing this. So this is phenylethanone. Why am I calling it phenylethanone? Because this would be like ethane because of the two carbons, but because of the functional group of carbonyl compounds, basically the ketone. Having this functional group of a ketone, ketones end with on. So it can't be phenylethane, but phenylethanone. Why phenyl? The benzene ring. Very excellent. So now, when you're outlining the mechanism for this reaction, it is as simple as this. Now, when we are outlining the mechanism, we just begin with this acid chloride reacting with the aluminum chloride. So we shall have our CH3, COCl reacting with aluminum chloride, forming, we shall form our iron CO, or one can write it as, then I call it, let me call it partially positive. Then we shall also have aluminum chloride, which is partially negative. So we are having partially positive ion, partially negative ion. Then now, it is this one that will work as your electrophile. So you're going to bring this electrophile and it attacks the ring. How does it happen? Bring a benzene ring and bring your compound, CH3, C, double bond, partially positive, then aluminum chloride. So this bond will come as this one gets off. So this one will lead you to form an incomplete, the ring, the benzene ring is disrupted, then the hydrogen will momentarily bond with the group you have introduced, which is C, double bond, CH3. So now what takes place here is that that aluminum chloride, which is not used, is the one that will come on hydrogen as hydrogen stabilizes the bond, as the bond stabilizes the benzene ring. So this one will lead you to form. Of course, the hydrogen has gone this side now. So we are going to have our benzene ring with the phenyl ethanol plus hydrogen chloride, and then aluminum chloride. So that is what we basically have for this particular case. So that is what we basically have. As simple as that. So the steps, we've realized that all the steps are the same, provided you have formed an electrophile. So the main point is to form an electrophile. The rest of the steps are the same. All right, so on this, I'm going to do you one more example. On this, I'm going to do you one more example, and then we call it a time. Shall call it a time. So let me do for you one more example here, whereby we are going to have benzene. We are going to have benzene. We are going to have benzene. This is my benzene ring plus my acid chloride, which is also a benzene ring, but it is an acid chloride though. So my halogen carrier is iron 3 bromide. So according to this, we are going to form our ketone, which is in this form. However, you can draw it in any way you want. You can keep like this, but let me draw the ones which are straight. So I will form my carbonyl compound. All right, then here I will have another benzene ring. So That is what we are having. So we want to see how the mechanism of this is outlined. Mechanism. This is very, very, very interesting. So if I'm to outline the mechanism of this, I'm going to first bring my acid chloride. All right, I bring my acid chloride, which is C double bond O, then Cl. So this acid chloride of mine is going to react with iron 3 bromide. And what takes place is that during the reaction, I'm going to form an intermediate. So I form the carbon positive center. All right, so this is my positive, and then I'll form iron. Remember, these ones cannot be made bromine 4 because this is a chloride, this is a bromide. So it will be iron, then 3 bromide, and then what is coming, which is the chloride. So what happens is now you bring your benzene. After bringing your benzene, this benzene will react with this electrophile. So you bring an electrophile. Now what happens is that the ring, this is my electrophile. Where? All right, so I'm going to bring my ring up to the electrophile center. Then from here, I am going to form the unstable ring. All right, so one can draw a circle, or as well, one can draw it like that and show that it is unstable. So there is a hydrogen momentarily bonded to a carbon. All right, we are having this, our electrophile. So what takes place is by losing a proton here, all right, by losing a proton, I'll form my final product. As simple as that. As simple as that. So members, let's ensure that we master this concept. Let's ensure that we master this concept. So for that case, as online students and as people who are following, I want to see if anyone can complete this equation. I want to see if anyone can complete this equation. And after completing it, I want to see if you can outline the mechanism. Complete the equation below. And outline the mechanism. So the equation is benzene plus CH3CH2 COCl in presence of aluminum chloride at 50 degrees Celsius. You're going to form phenylpropanone, but I want you to practice it out and then you see. So as a habit, we have already seen that these final products we form can be used to manufacture other products. So I'm going to use an example, phenylethanol, the one we first worked on, and maybe conclude with that by showing you where it is applied. So phenylethanol can be used to prepare phenylethene that can also be used to prepare or to manufacture plastics such as polystyrene. So basically, let me show you how phenylethene is applied. NB, let me bring it as my NB. That phenylethanol that we formed is used in preparation of, we can use it to prepare phenylethene, and this phenylethene can also be used to manufacture plastics, e.g., those plastics can include polystyrene. Now, let's see how. If you have phenylethanol, we had formed it as CHCOO, then CH3. So what you do, you first reduce this alkanon or a ketone, you first reduce it to alcohol. So the reducing agent we shall use is lithium, aluminum hydrate in presence of dry ether. We can reduce ketones or aldehydes, alcohols. All right, so we shall have it, since it is a ketone, then it means that it was oxidized from a secondary alcohol. So for us, we reduce it to, it was oxidized from a secondary alcohol, or it was formed from a secondary alcohol. So when you reduce it, still it goes back to secondary alcohol. So we shall have CH, OH, CH3. Then now, after getting an alcohol, of course, you know the hydration reaction of alcohols. If you add concentrated sulfuric acid at 180 degrees Celsius, you're going to form your end product. So our end product was CH, or is CH double bond, CH2, CH double bond, CH2. And this is called the it is called phenylethene. Is phenylethene, or one can call it styrene. You can call it phenylethene or styrene. I wish you all the best, our viewers. I will love it when you comment. I love it when you share to colleagues, and I love it more when you subscribe. See you next time. Stay blessed, and thank you for watching.